Hello everybody. We are here for the new Continual AI learning seminar session, and today we have Nicolas Ray from University of Texas at San Antonio, and he will talk about his recent paper called TACOS, Task Agnostic Continual Learning in Spiking Neural Networks. So there are not many works around talking about spiking neural networks in continual learning. There are some, I would say, but this is a new, hopefully very interesting one, I think. And so I hope you can all enjoy the talk, and we will reserve some time at the end, as always, for the question answer. So prepare your questions for Nicolas. Nicolas, the stage is yours.
General category that I want to kind of highlight is ReplayRehearsal, which typically, you'll either have some form of a data buffer or a generative model, and you'll allow the network to experience simulated data from prior tasks or specific examples that were stored from prior tasks to retrain the model and let it remember kind of what it's seen in the past as well as what it's currently learning, to kind of mitigate the catastrophic forgetting or interference that would occur. And this is probably the most well-performing approach overall. It kind of directly allows the network to learn from all tasks mixed together, directly addressing that IID distribution of data problem that you have with continual learning tasks. So just to kind of summarize them all together, in terms of dynamic architectures, we have the structural plasticity where you're changing the size of the architecture or gating. For plasticity and regularization, you have things like synaptic consolidation, metaplasticity, and local learning. And then for replay, you have rehearsal and pseudo-rehearsal. And you have some features in the brain that also kind of intermix these two. So for example, between dynamic architectures and plasticity, you might have some form of neuromodulation that's kind of doing both, or you might have some form of recall and consolidation at a memory level and a synaptic level. So each of these approaches, has their own benefits and cons, or pros and cons. And we're not saying that any one in particular is the one solution to solving continual learning. So with dynamic architectures, you're adding neural resources over time, so your network can grow unbounded. You can address this with methods that involve pruning or fixed sizes, but still then either you're selectively forgetting or you still have a limit to how much you can grow. With metaplasticity, it's nice because it doesn't require too much overhead to a network typically, but at the same time, eventually you will end up restricting all of the synapses plasticity, and you'll reduce learning on future tasks. And then with rehearsal and replay methods, you can allow the network to see previous experiences and retrain on it, but this requires an offline learning phase. You might have limited storage capacity or limited performance of a generative model. And you need some time, if you're talking about edge devices or streaming devices, to kind of go offline and, disconnect from the real world environment to learn on their own. So each approach has its own features and benefits. And we specifically, when we were thinking of hardware-friendly edge devices, we targeted this plasticity kind of features because they can integrate directly with the network itself. You can kind of just impose them as some kind of loss rules, technically, and they can be used in online learning. And so when we talk about our work, we kind of focus in that kind of setting where we only see a sample once. We're learning from one sample at a time in kind of an online fashion. And so we'll talk more about that later. But so the proposed TACOS model, I'll quickly just talk about why we like spiking, why we wanted to look at the spiking, kind of paradigm for this problem, and then explain the architecture and then some of our results that we published at ICML. So real quick, a brief introduction to spiking. We're not going to get too into it and the math behind it, but instead of your traditional rate-based neurons, which receive some input stimulus and produce an immediate activation, like a ReLU function, you're given some value, you produce that value as long as it's greater than 0. Spiking neurons are inherently recurrent, so they have some temporal aspect where their activity depends on their previous state. And what they do is they integrate binary spikes over time until they've accumulated enough in which they emit their own spike. So the reasons this is kind of useful in continual learning that we were looking at was that it was complementary with local plasticity mechanisms. You have the sparse temporal spike trains, which can kind of localize the learning process. It doesn't need gradient descent. And research has been continuously going on where new training methods have been proposed to address the disparity that has been traditional between spiking and artificial neural networks. And they're getting very good in kind of the simple feed-forward MLP architectures, and in the last few years, they've also been getting better at training convolutional neural network architectures with some of these surrogate gradient rules where they approximate kind of what would occur with backpropagation, but related to more Hebbian-like learning. Aside from the algorithmic side, we're also focusing on, the end goal is to have this on-edge systems where energy efficiency matters and spikes can be very low cost for communication. They can be sparse if you impose constraints on the spiking neurons themselves. And they have very efficient communication when you use binary spikes, which is just a simplistic model of what a spike is. But by making them binary, 0 or 1 events, they're very easy to communicate across layers, and they're very robust to noise if you're working in analog systems or something like that. So our specific problem, we thought that, most of the continual learning approaches we had looked at, which has been changing now, but were not task agnostic, which was a big feature we thought for if you wanted truly deployable system or practical system to operate on its own. It won't have that Oracle providing task information, especially in the spiking field. That wasn't really a concern. Additionally, most, if not all, of the works we had looked at for spiking neural networks relied on Hebbian learning. And Hebbian learning is great, but it doesn't do well for task-specific learning beyond the single layer. So we wanted to see how can we combine, some of the newer learning rules for spiking neural networks that are training these multi-layer SNNs with other features or models of plasticity in the brain that can help address continual learning. And so we look at different heterogeneous neuroplasticity mechanisms and see how they can aid in continual learning, keeping in mind the goal of an energy efficient way. And so the solution that, kind of TACOS combines is using local plasticity, so we're not relying on task knowledge. I mean, we have it's supervised learning, so there's still an error signal for the specific task labels. But it doesn't know which tasks the labels are coming from. It's sparser updates and low communication overhead. We introduce complex synapses. So we exploit a combination of a heterosynaptic decay with consolidation and metaplasticity to mitigate catastrophic interference. And importantly, for practical applications, the model size does not grow as a function of the number of tasks. And then spiking neural networks, as I was talking about, can be very energy efficient with the cost of a single spike. So kind of the baseline network for how we learn a task, we train it using a learning rule for spiking neural networks called event-driven random backpropagation. So the way this model works is that you'll have some output spike train, which is binary events of 0s and 1s coming from your output neurons. And you can compare that with a target spike train. And you can feed both of these spike trains into another set of spiking neurons, which will either detect false positives or false negatives, and they will randomly propagate that information backwards to the hidden layers. So there's no direct backpropagation through the network. Instead, we have this form of random feedback where the error gets sent backwards to each neuron and accumulated, but that error is kind of just a random combination of the output error. And what we do is we accumulate this error in a second compartment. And when a presynaptic neuron spikes, we update the connection between the pre and postsynaptic current based on the accumulated error. And so this update rule is kind of friendly in hardware because it comes down to just a logical condition. Did presynaptic neuron spike? Was the postsynaptic current within some range of values, which is a surrogate of approximation for what would be captured by the derivative in backpropagation? And then if those two conditions are met, we update the weight based on the accumulated error. So this by itself will still suffer from catastrophic forgetting. And it's actually worse than Hebbian learning at continual learning, just because, you know, it's more of an approximation of backpropagation than it is of a local learning rule. So if we want to use this model to get, you know, better performing SNNs, and we want to keep moving towards continual learning, we need to introduce some new mechanisms. So the first one that we look at is metaplasticity. And metaplasticity, you know, it's been around. It's the plasticity of plasticity, where, you know, you're controlling how much a synapse can change, almost like you're controlling its synapse-specific learning rate. And the way we do this, you know, we have a metaplastic state that determines the plasticity based on, you know, its own metaplastic state and the strength of the weight itself. So in biology, the way this works, you know, is you're kind of changing the physiological or biochemical state of a neuron or synapse, and this will modify the changes induced by synaptic plasticity later on. And so there's different approaches which can be local or global control of the network itself, and so working at a very local, very specific to that individual synapse approach. And once metaplasticity is applied, you know, future events can have very little impact on that synapse. So our specific model, you know, as I'm saying, our goal is to kind of allow a reduction in synaptic plasticity based on a neuron's importance. But unlike some of the approaches we were comparing at the time, you know, we wanted to estimate importance using local information, so online, without task knowledge. So to do this, we estimate the importance of a neuron based on its firing rate at that time. So it doesn't need to know what a task is. It just knows that during a sample, you know, the neurons that fired the most were the most important. And so the synapses connected to those neurons were the most important. So then to compute the degree of plasticity, you know, we have just some function that's a function of both the metaplastic state M and the synaptic weight W. So, you know, important neurons will end up having lower plasticity because they'll have a higher M, and the synapses that were contributing to that task or to that neuron's response will typically be larger in strength, and they'll also have reduced plasticity. So if we looked at the curve, the plot on the left here, you know, you'll see that on the bottom, as synaptic strength increases, your learning rate or degree of plasticity, scaled from 0 to 1, is decreasing with the magnitude of the synapse, and the absolute value of its magnitude. And similarly, as M becomes larger, that rate of decrease becomes faster. So, you know, with a very small M, you know, as the synaptic strength changes, there's almost no restriction in plasticity. But with very large M, you know, as soon as that synapse learns a little bit of information, it's almost immediately frozen. It's regularized so hard from learning in the future. And then to adjust M, as I was saying, what we do is every time the network experiences a sample or classifies on a sample, we look at the presynaptic activity and the postsynaptic activity of the neurons, and if they were greater than some threshold, we say that, you know, this synapse was active and we're going to increase its metaplastic state. So this approach requires an additional parameter for every synapse beyond just its weight, the metaplastic state, which can be lower precision than a synapse itself. But it can be reduced to a value for every neuron rather than every synapse, with getting similar performance. And that's kind of something we want to explore trade-offs of in the future. But the second combination that we had to add to metaplasticity, because metaplasticity by itself wasn't sufficient or wasn't, you know, strong enough to really compete with the state-of-the-art approaches, was synaptic consolidation. And so, you know, the idea behind consolidation is that, you know, we're learning things on a short-term scale, and then we consolidate some of this knowledge, over a longer time scale into something we call reference weights. And so now, your synapse consists of, your synaptic strength W, which is used for your normal feed-forward process and inference, with this metaplastic state governing its learning, and now this synaptic consolidation reference weight, that's kind of trying to retain information and remember what have I previously learned, what was important, and to pull the network back to that state. So kind of the basis behind synaptic consolidation is that you'll have some stimulation of a neuron where it will start to learn things, but it will decay. But over time, with late phase LTP or with strong stimulation, you'll consolidate and maintain those changes to the synapse. And we capture this by using a model where we have the fast component and the slow component to a synapse. So your fast component is your normal weight that's updated by ERBP. So this equation that you see, where is just S of J is the presynaptic neuron, UI is the postsynaptic neuron's accumulated error, and the theta I is just the boxcar function for if I is within some range. So 0 or 1 if the postsynaptic current meets some criteria. So that's just the ERBP that we talked about in the beginning. So it's driven by task-specific learning, and it's modulated by metaplasticity. Now, the slow component that we're adding is, a reference weight that's only job is to follow or slowly approach what your fast synapse is over time. But it's on a much longer time scale, so it's slowly moving towards that weight. And so it's just pretty straightforward. Your reference weight changes based on the difference between your fast weight and the reference weight itself. But what this will do is we'll kind of track the learning that's going on with the neuron over a much larger number of samples. And you can set this up to, if you know the number of samples per task, so that it's learning at different rates, and you can explore what happens if it's controlled to learn, at a very small portion of a task for half a task, if it follows kind of so that it's tracking what's learned during a whole task or across multiple tasks. And you can kind of explore the different dynamics that occur. But what we wanted to allow was that this slow component needs some way to interact with the fast component, right? It does nothing. It's just there by itself saying, hey, this is what you used to be. And so to allow that to happen, we have something called heterosynaptic weight decay. And this allows this kind of bidirectional communication between the fast and the slow component, where, if a postsynaptic neuron spikes, meaning that this synapse is actively contributing to the current task, it's going to be changing its weights, then we're going to also have some form of decay where we're telling him, hey, here's what you want to learn now, but here's what you found optimal after learning over X amount of period of time. Here's the kind of the state that you had arrived at. And we add some form of punishment to kind of try to maintain that state. And so kind of small sporadic changes that might be caused by noise or odd samples, it might be filtered out by this approach, whereas very persistent long-term changes will still be captured. So the whole model in itself, is essentially focused on adding this complex synaptic model to ERBP. So there's not overhead in terms of the number of neurons, but for every synapse, we now have an additional weight parameter and an additional metaplastic state parameter. And we'll kind of compare, how much overhead that is compared to other regularization approaches later. So the two data sets we use to just test this work were split MNIST and split fashion MNIST, where we, you just kind of take your classes in the data set and you put them into pairs, and you make each pair a different task. And the goal is to just classify, is it pair 1 or pair 2? And we did this for both MNIST and fashion MNIST in a domain-incremental scenario. So the output layer is shared between the neurons. So it will never need to know the task identity during both training and inference. The goal is to move it to where it can also tell you which task it is, but currently we weren't focused on that approach, and that's kind of where we're going now. But importantly, TACOS only sees each sample once. One training epoch, which is unlike, most of the other approaches. They didn't do as well with lower training, or with only one epoch. And the architecture specifically used for these results, was every hidden layer consisted of 200 neurons. The output layer has 2 neurons, one for each pairing. And then we looked at just 1-layer and 2-layer results. And we compared that with some of the other regularization approaches in continual learning. So, from this table, we can see that, TACOS for both FashionMNIST and MNIST was able to get state-of-the-art compared to other regularization models, with relatively low standard deviation in performance. Some of the important takeaways beyond the fact that it was performing with rate-based models that are trying to aid in continual learning in a similar way, is that when you compare it to obviously just a baseline spiking neural network with the RBP, there's a significant improvement. But even if you only take the metaplasticity by itself or the consolidation and decay by itself, the performance gains are minimal. They're nowhere near other approaches or the best that TACOS can do. And interestingly, by itself, synaptic consolidation doesn't actually show much, if any, improvement over, a baseline performance in continual learning. But when we pair that with metaplasticity, it shows a very significant jump in performance. And then when we look at the memory overhead to see, kind of just a quick estimate of how expensive our method is compared to other approaches, TACOS by itself is roughly 2.5 times more parameters than just the baseline model, which is pretty similar to other approaches, but it is slightly bigger than a few of them. Specifically, Learning Without Forgetting and SS. Oh gosh. Sorry, I'm blanking on names right now. I don't know why. But so to kind of explore the learning dynamics of TACOS, we wanted to look at, kind of how is the plasticity stability trade-off occurring? How is it learning on tasks, forgetting? Is there any form of forward transfer going on or backwards transfer? And other features like that. And so, we thought the easiest way to kind of see it, although it's still actually very messy when you have so many lines, was this kind of plot that shows the performance of all 5 tasks after learning a specific task. So the gray bar shows you kind of, what task you're learning. So if you're to the left of the gray bar, you're looking at the performance of the task after you've already learned it. And if you're to the right of the gray bar, you're looking at performance on a task that has not yet been seen. And so we're just seeing, how would it do looking at that specific task test set. So what we did was we kind of compared, TACOS, where we put different constraints on the maximum metaplastic state, because as I was saying earlier, if your metaplastic state grows unbound, all your synapses will become frozen. And that's not something that you want to occur. So at some point you have to limit it and then say, this is just our model with its maximum restricted plasticity, still trying to learn new tasks and retain old information. And we compared that to, another approach that used a very similar metaplastic, model, or the where we were inspired for this metaplastic model from, actually, where they used a fixed metaplastic state. So instead of allowing this metaplastic level to change over time, it's a global metaplastic state determined ahead of time, and then the dynamic part is just the synaptic strength. So what we can take away from this plot was that, TACOS, it showed a much better retention in task performance over time. So if we look at how task 1 changes over time, where blue represents TACOS, we can see that for the most part, except for the very low metaplastic state where you kind of reducing the impact of metaplasticity to almost none. TACOS shows a much higher retention and performance than any of the fixed metaplastic models of the baseline model. And that performance holds true generally throughout the plot, or throughout all the tasks. But what we can see is that even by task 2, is the baseline SNN is always achieving a higher single task accuracy. So when you're learning that specific task, your SNN, which is not restricted, is able to learn that task better than either TACOS or a fixed metaplasticity approach. And this shows the, inhibition to learning that occurs because of metaplasticity. And so we kind of wanted to understand where those limits lie and how can we address this in going forward with future models. So one way of trying to look at this a little deeper, both to compare why this activity-dependent metaplastic approach could be better than using a fixed metaplasticity model, and to see, what is actually happening to the plasticity of the weights. We look at, how much plasticity is allowed in the network by these different approaches by kind of measuring the average change in weights from task 1. And we also see, by the last task, how much learning is still allowed. And that's just by measuring the average change in weights from learning task 4 to learning task 5. And what we can see, interestingly enough, is that, for your input weights, the high metaplastic state of TACOS, it doesn't have too much impact on your overall weight change. But we can see that, with a lower metaplastic state where m equals 5, you do have slightly higher amount of plasticity allowed than when m equals 50. And when we compare that to a baseline SNN, we can see that it's almost 1/3 of the overall plasticity. So that's actually a very significant, reduction in the amount that the weights are allowed to change, or that they would have changed just driven by AirBP alone. And that reduction is both the reason we get improved retention and the reason we get, reduced single task performance. So it's a very fine line. But when we compare it to the fixed metaplastic model, we see that you can't have high metaplastic states with a fixed metaplastic approach. You're kind of restricted to lower metaplastic states. And even at a similar, low metaplastic state, there's a lot less plasticity when compared to this activity-dependent TACOS version, because your metaplastic state starts off at 0. And so early on, at least, it allows for much more learning, which is reflected in the overall, larger number of plasticity. Whereas by the final task, the plasticity between a fixed approach and TACOS is pretty similar. At the same time, we also wanted to kind of look at the cosine similarity of hidden layer activities, and this was kind of giving us a sense of, a quantitative value to see how well it retained information or reflected or was able to produce what it had learned when it first learned a task compared to after learning all tasks, right? So, what we did was we said, okay, task 1 consists of the digit 0 and the digit 1. Sorry about my dog. He gets a little anxious when I give talks. So task 1 consisted of the digit 0 and the digit 1. We looked at the average hidden layer activity of those two classes after learning task 1, and we stored that average pattern. Then we trained on all 5 tasks, and we again looked at what was the average hidden layer activity towards digit 0 and digit 1, right? And we compute the cosine similarity between those two hidden layer patterns. And so you can see, is that the higher the metaplastic state, for TACOS, the larger the cosine similarity, or the greater the retention. And it's larger than an SNN. And between task 1, or between digit 0 and digit 1, it's always better than SNN, no matter how low TACOS gets. Although, for digit 0 specifically, It's pretty close to the SNN value. And we believe, when we looked at kind of the overlap or the similarity between the digits themselves, is because the digit 0 had kind of more overlap across all the learned representations, specifically in the way that it was paired up against other numbers. So the neuron responsible for 0, which we'll just say was neuron 1 in the output layer, had a lot more overlap with neurons that had a high, or with digits that had a high kind of degree of overlap with the number 0, but belonged to neuron 2. And so it's not in these slides, but we also looked at how, reordering these tasks based on, the similarity between numbers. So you try to put all the numbers with, the greatest similarity or overlap in the input space to one neuron and the others to the other neuron, or to do the opposite. So where you're trying to create the most interference really changes your results. But that's going, outside of what we're going to talk about today. But so, TACOS, it shows a higher cosine similarity compared to the SNN, and the higher the metaplastic state, the better. Whereas, we're not going to focus on the fixed metaplastic states for high values where 50 and 25, which is because at those two states, it doesn't learn. So there's kind of a high similarity because there's almost no changes to the weights. There's still a few, but it's very, the performance is poor. The accuracy is very minimal. But with lower metaplastic states at a fixed metaplastic approach, you actually do see almost a better retention in tasks. Not when m equals 5, because that's kind of too low to have an impact, but when m equals 10 in the fixed approach, at least for digit 0, surprisingly, it does well. But then digit 1, it did not. And we weren't sure the reason for that. But we believe that the reason it did well for digit 0 early on was because from the very beginning, it had a high restriction to plasticity, whereas TACOS did not. So then the last kind of stress test we wanted to look at, and this kind of shows what I think is one of the bigger limitations with this approach, is how TACOS works with reduced data set sizes. So to find the parameters for all of our models, we threw this into genetic algorithm and said, I'm not worried about how realistic is this value to the brain or not. I just want to know which values are going to give me the best performance. And so for the full data set, I found the set of parameters where you learn for one epoch and you get X result, which was competing with state of the art. And then when you reduce those numbers to, the number of samples to almost half the data set, a little bit less, there's a slight degradation in performance. And so what we did was we tried to, and that's shown by the red bars. And so what we did was we said, well, can we scale the metaplasticity and the synaptic consolidation so that their effects are kind of equivalent to what it would have been with the full data set? So basically, we're making it stronger. And you see that improved it a little. And then when we decrease samples to 8,000, you see a really large drop in performance, in the unscale approach, where we use the parameters found by the GA. But when we scale those parameters based on what they should be by the drop in number of samples, that performance recovers. And this is reflected again from down to 2,000 samples and down to 800 samples. So the point being, the ability of metaplasticity and consolidation to effectively, identify important synapses, protect them, and at the same time consolidate long-term information over time is very dependent on how long you're going to be spending learning that specific task. And so kind of the work I've been doing now is addressing this concern with a more dynamic approach where, when I showed the metaplasticity model earlier, your metaplastic state, if it meets some criteria, was increased by a fixed amount. And what we're changing the approach to how we adjust metaplasticity and how synaptic consolidation can be controlled in conjunction with the metaplastic state to kind of allow for this more, dynamic approach that applies very high, metaplasticity and consolidation early on, but quickly drops down in strength, so that you can kind of get the same effect of we can learn quickly, but we're not going to overshoot and kind of freeze the network after just 10 samples because we want it to kind of identify important synapses too fast. And then somewhere, we began to look at omniglot. We didn't do any actual tuning towards omniglot or we just, we took the network that we used for MNIST and applied used those parameters, architecture, everything, and just said, if we make some easy synthetic 50 task split omniglot data set with 5 classes per task, which just consists of random characters, how does it do over time? And so this is kind of harder with one epoch because the model's not geared towards few shot learning, and so it's only learning on one epoch, where one epoch consists of 15 samples of a certain character. So there's still a lot of work to be done with this case in particular, but what this test still showed was kind of what we expected, right? And just kind of confirmed some of those things where, even after 50 tasks, you can see that the low metastate does better than a baseline SNN, and I don't mean low as in like non-negligible. I mean low as in where it's functioning but not too high. So that's not very specific at all. But basically, a high metaplastic state was specifically chosen to be a very high value where you would quickly retain information and then become unable to learn after a few tasks. Whereas, the low metaplastic state was geared towards a nice balance between not learning anything and retaining information over time, and forgetting everything. And so what we see is the low metaplastic state has a higher baseline accuracy, whereas surprisingly the high metaplastic state, kind of actually has the same performance as the SNN. But more specifically, when we look at the single task accuracies over time, we can see that the baseline SNN and the low metaplastic state are very similar, whereas a high metaplastic state very quickly can no longer learn in comparison to what the previous tasks did, except for the cases where there's a good amount of overlap between the current task and something it learned previously and remembered, and that's where you see these high spikes in performance. But then conversely, when you look at first task accuracy, we can see that the SNN completely forgets the first task much faster than both low and high metaplastic states, whereas the high metaplastic state retains that information much better than any of the other approaches or the other two models. But there's an interesting situation where you can see low metaplastic state surpasses the high metaplastic state's performance, and that's when it kind of allows some form of backwards transfer. So what we're saying, if we look at this kind of task 34-ish, the task it's learning at that time actually, has information that can boost performance on task 1, the first task it learned. But the high metaplastic state, which has kind of completely eliminated forgetting for a more, consistent retention of knowledge, can't benefit from that backwards transfer, whereas the low metaplastic state still can. But then conversely, if we look at task 44, it can also suffer from a much stronger interference. And so kind of taking this further and exploring, how TACOS does over a much larger number of tasks, with different degree of sample sizes, and how we can address this, kind of dependence on the number of samples and tasks in its parameter settings, is what we want to do. So in conclusion, this was kind of the first demonstration of a spiking neural network that wasn't relying on heavy learning and was scalable to, multiple layers, to more NLP-like architectures. And it demonstrated state-of-the-art performance in domain-incremental continual learning, which was achieved through local plasticity functions, important, which they don't require task information, they don't grow with the number of tasks, and they're only trained on a single epoch. And we thought it was kind of important to show that, in comparison to existing works, this kind of adaptive metaplasticity that allows for an online estimation of importance is, much better than a fixed metaplastic state, but at the same time doesn't need task information to kind of estimate that importance. And that from ablation, we showed that it really needs both this metaplasticity and consolidation together to compete. And so moving forward, besides addressing those challenges that I was talking about on the previous slide, we also want to apply this to more challenging scenarios. In the last couple of years, these surrogate gradient learning rules for spiking neural networks have started to been applied to CNN-like architectures, as I was saying earlier. And so trying to look at some of those frameworks and models and how to integrate TACOS into that, as well as reinforcement learning environments would be, greatly beneficial to really comparing this to other models beyond just the MNIST fashion, MNIST domain, which, us and our prior spiking buddies were kind of restricted to in our continual learning analysis. So that was all. Here's the references. They'll be in the slide deck that's shared live. And I believe the paper was linked, or we have the link to share to where you can find it. And we would like to acknowledge, the Air Force Research Labs and DARPA for sponsoring parts of this work. And thank you for your time.
Thank you, Nicholas, for the amazing presentation. Just wait for a moment. I heard my voice back. Can you try to shut down your microphone? Let's see if this helps.
Yeah. Let me plug a headset in.
Okay, yes, maybe that was. Okay, now it's gone, I think. Yeah, perfect. Thank you. Can you still hear me, right?
To the headset. See, I don't use Teams that much.
Okay, now I can hear you back. Can you hear me?
Yeah, I can hear you.
Oh, great. So thanks again for this presentation. I really hope to see future works about this, because it seems to me that there is lots going on here with the model and the online learning scenario, the spiking, metaplasticity and so on. So it would be really great to see future extension, exploring more deeper these aspects of continual learning, which I think are not so generally studied, especially in spiking neural networks, right? As you were saying before, there are not many works on spiking neural networks, unfortunately, I would say, in continual learning. So by the way, we had a bit of a problem with the YouTube stream, but fortunately the audience should only miss the first minutes in which you were introducing the continual learning approaches, so nothing related to your specific approach. So hopefully the video stream will be fine for the rest. And this gives me also the opportunity to remind everybody that you can always join our Slack space, in which you can find the link to join directly here on Teams, so that you can always hear at best quality the speaker. But anyway, sorry for the initial inconvenience. Okay, so I can start with a question while the other people are preparing their own. I see that yes, we have already questions from the YouTube, so this is great. But just to break the ice, I was wondering if you can share with us the tools that you use to do the experiments, because I mean, for people already involved in spiking neural networks, it's quite easy to set up these experiments. But I think that at the very beginning, one of the most problematic aspects are the training time, of course, because being a more complex and powerful model, it costs a bit more to train a spiking neural network, but also the practicalities of the experimental setting. So like the libraries, the architecture that you use. So how do you choose the architecture? Is like the same way that we did in machine we do in machine learning, like try, see results, guided by some experience, or there is something else going on that you can leverage to select the units, layers, and so on?
Yeah, so specifically for me, I kind of wrote all of this from scratch in MATLAB and Python. I like having control of just all the functions, and for me, I find it faster than learning to use kind of other toolboxes that are available. Most groups that are doing these surrogate learning rules and applying the spiking neural networks to CNNs, it's all in Python, and it's using either kind of TensorFlow and some of their own libraries, or it's using Brian Simulator or some newer models that are coming out. But I intend, like, there's something called SNN Torch, which is what I was planning on moving to do my own TACOS work with spiking CNN. But so for this work specifically, it's all just kind of from scratch code in Python and MATLAB that don't really have any dependencies other than just normal NumPy. There's not too much to it. We are planning on open sourcing our approach and our model on GitHub, kind of as I publish the concerns that I was talking about towards the data set scaling problems and other factors. So if people are curious as to how we did it, our approach will be on GitHub, which you can find from the new AI Lab website. Otherwise, there are some spiking simulators, especially that are coming out quickly. Most of them work with Python and then have other dependencies. And those are also useful to check out and can save you time. But as far as, addressing the size of the network, specifically in this approach, I did it based on the number of neurons that were used in the other regularization approaches we compared to. So most of those works had, hidden layers with 200 neurons. They either used 1 or 2 layers. And so that was kind of like why we fixed TACOS to that size for this work specifically. So I don't know how it would do with other layer sizes, or if it would do better or worse, etc. When I'm doing my own other work where I'm not worried about comparative performance to other models, I usually run either a genetic algorithm or just try to intuitively, set a small sweep and go from there based on what I see and what it's doing.
More or less there is no free lunch in spiking neural networks either, I believe.
Yep.
Thank you very much. So just another question coming more to the continual learning topic. So what are the main problems, if there are any, of course, that you see in scaling these methods and TACOS to different benchmarks and also maybe different scenarios like class incremental or other scenarios in which you, let's say, you add new knowledge also in the famous output layer of the network, which has been proven difficult for regularization strategies.
Yes.
Without any further, let's say, further approaches, but something like avoiding all the softmax that we use in the output layer. So spiking neural networks may provide a way to avoid to classify only in this way. Are there any local rules for classification or something like that can surpass the limits of regularization approaches for class incremental learning?
Yeah, so I've been hoping that was the case, and I haven't had any luck with that yet.
Okay.
So what I found was with the spiking models, when you apply it, using this regularization kind of approach to the class incremental scenario, what's happening is, for me, and I didn't share this in here, post it or anything, but was that TACOS would learn the last task, and then no matter which sample it saw from any task, it would always go to one of the last task's neurons, because they would never have been inhibited from firing to those classes, whereas the other neurons, even if it slightly showed some degradation in their weights overall, which reduced their firing pattern enough to where the last task neurons still win. So what will happen is, if you have digit 0 and you present 0 to the network, maybe the neuron for digit 8 will fire the most, and then digit 0's neuron will fire the second most. But it has no way of saying it was 0 over 8, even though it was. And so how to address that is kind of something that I want to solve, because that is a very important issue. And it's definitely a much harder scenario and a much more practical scenario. And so one thing is I kind of chalk it up to just issues with regularization approaches limitations. And I don't think, so when I was talking about all these neuroplasticity, or all these neurally inspired mechanisms for continual learning, plasticity regularization being one of them, but it's not the only one, and I don't think any solution should rely on one. And so like the way I saw it was it's some kind of nice combination of things where you can have some form of dynamic architecture gating that's balanced, or you can have some kind of regularization approach that's aiding in online learning. So while a system is learning online, it's not forgetting information, and it doesn't need rehearsal or replay to kind of retain that information. But when the system has free time or goes offline, like when we sleep, then you can apply these, rehearsal replay methods, which show much better performance on the more challenging class incremental solutions. And you can kind of use some balance between these two, because you can't always take a edge system offline and batch the data and train it on, all its previous samples. But if you can have some kind of online mechanism to prevent forgetting, or to reduce forgetting during the wake hours, and then tie it to consolidation and rehearsal or replay, that might just be a very feasible and kind of simple approach almost. But so in my mind, I've been looking at kind of moving beyond just regularization and combining it with either just some form of the dynamic architecture gating kind of approach, or if that doesn't work, maybe it is rehearsal is the best choice for combining. But yeah, so I don't know, and I haven't seen anything inherent to spiking that overcomes that regularization challenge. But yeah.
Yes, exactly. So replay is usually the sword which we use to solve this problem, but there has to be something better, in my opinion. I remember that.
Right. I just don't know it. So out of what I have now, that out of what exists now, that's my this is how we can deal with what we have. But it's got to be. There's more to it. I mean, there's lots of stuff just in the brain that we don't fully understand, and there's a lot more bio-inspired mechanisms that are way beyond what I talked about here, and beyond just the neuron synaptic level that I haven't even begun to explore. So there's a lot of areas we can look for answers into, how we might overcome some of these limitations right now, without relying on replay. But yeah, I don't know it well enough to give anything more than just, I can quickly make this work if I combine it with replay.
Yeah, that's for sure. I remember that I read something about this, and I think I will be able to find this paper, and maybe I can share with you on the forum or in any other way, which claim to surpass this problem on the output layer with a spiking neural networks by using something like winner-takes-all approach. But it wasn't very clear to me actually what they did. So maybe we can.
Yeah, that would be interesting. I didn't read that work. I was trying something similar. with a kind of almost like a winner-take-all approach and something called synaptic scaling. But I didn't spend too much effort because I didn't put my focus on the classic incremental scenario. As well as I was just kind of happy that TACOS worked on domain-AI, but I wanted to solve the problems I talked about first before moving on to
of course.
But I'd want to look at that paper though. It sounds interesting.
Yeah, I will find it out. I'm sure that I have it somewhere, like in my Zotero or something. But I will share with you the paper.
I appreciate it.
So yes, you basically have a twin that mailed you the question from YouTube because you already answered it while you were answering my question. So there was a question on YouTube asking about replay methods, how can be combined with TACOS, and if in case you would use a lower or higher metaplasticity. I don't know, maybe this last part has not been completely addressed, but I don't know if you have any thoughts about metaplasticity with replay, how they influence each other.
Yeah, so I think, if you wanted to, I showed that high metaplastic state very quickly can freeze a network, but but it can retain information well. So if you're taking advantage of replay frequently enough, one idea would be, you have a high metaplastic state, high change in metaplasticity, so that you're rapidly locking in and retaining information, but then when you apply rehearsal, you reset it. So it'll be kind of like, very quickly, this is what I just learned, I'm going to try to remember this. This is what I just learned, let's also remember this. And then, okay, here's all my knowledge. Let's find a kind of optimal state among everything I've learned and readjust for the next day. So I think it would work best with that high metaplastic state and a kind of a reset applied once you apply rehearsal. Whereas if you did the low metaplastic state, you wouldn't be getting as much advantage from it because you still have that rehearsal going on to kind of do the same thing. And over a long period of time, all it's going to do is slow down learning. So that was kind of, when I had thought about this issue, my thoughts on how they would tie together.
Okay, great. Are there any other questions from the audience here also? Feel free to unmute yourself in case. Or write in the chat. Okay, if there are not any more questions, let's thank Nicholas again for this amazing talk. And I remember everybody that the last ContinualAI seminar will be the last for the year, because in the next weeks we are starting to publish the ContinualAI continual learning course sponsored by University of Pisa, the Doctoral AI Academy course. So basically each week you get 2 lectures on continual learning, introduction to continual learning from machine learning perspective, but I mean you can follow the course even if you're not from the strict machine learning background. So yes, that will be more or less the content up to the end of the year. And then of course we will come back with the continual learning seminars live with new speakers and new papers. But until then, there is already another one on next Thursday, so be sure to join us, and I'll see you all there for the next seminar. Thank you all, and thank you, Nicholas. Bye bye.